And so first, I would love to introduce my colleague here at Georgetown, Sarah Adele Bargal. Sarah is an assistant professor of computer science and the Provost Distinguished Faculty Fellow at Georgetown University. Sarah's research interests are in machine learning, computer vision, and explainable artificial intelligence, with a current focus on making artificial intelligence systems explainable and accountable to humans and society. I was telling some folks at lunch that our team was just laughing so hard when Sarah and I were brainstorming on some content ideas of what to share with you all. So I hope you all will enjoy Sarah's talk just as much as we did. So Sarah, come and join us. And the clicker.
All right, good afternoon. I'm Sarah. I work on computer vision, and our slides tend to be heavily image-based, so I think that was strategically scheduled for the after-lunch session. We'll try to keep it light. All right. So I'll start by discussing three terms that are used pretty much interchangeably nowadays, and I'll start by giving a little bit of guidance on when we use which term, and the three terms are artificial intelligence, machine learning, and deep learning. So artificial intelligence is a technique that enables machines to mimic some kind of human behavior. So even, the first GPS that was out there that allowed us to, get the shortest path between points A and point B is an artificial intelligence algorithm, despite the fact that it does not use any data. Now, an algorithm is specifically called a machine learning algorithm if it learns based on human data. So nowadays, when we use our GPS, we say we'd like to, the shortest path from point A to point B, but we also specify things like we would like the least traffic. Now, the way we get the least traffic is by using other people's data, right? All the cars, where they are located, etc. We could also ask for the route where we could, pass by a coffee shop that has at least a 4.5 rating, right? That's again using data, and so that would be classified as a machine learning algorithm. Nowadays, most of the state-of-the-art algorithms lie inside this machine learning bubble, which we call deep learning algorithms. So a lot of the technologies that we're using and seeing nowadays are in the last bubble you see right there, which says deep learning. Deep learning is based on deep neural networks, specific architectures that are trained in order to perform particular tasks. And these networks have been performing extremely well nowadays. This has been happening now and not in 1958 when the perceptron or artificial neuron was first introduced, because of three main reasons. The first reason is we did not really have big data at the time. So the first, we can say, large-scale data set that was introduced could be ImageNet or Wikipedia, right? Social media networks. ImageNet was proposed in 2007. That's way after the perceptron has been proposed. Also hardware. So there wasn't the hardware we have today. So today we have GPUs, graphics processing units, that allow this high dimensional data, a lot of it, right, to pass through these models that have millions and billions of parameters in order to be able to perform very complex tasks that are very similar sometimes to human cognition, identifying particular objects, whether there's a pedestrian crossing the road in front of an autonomous vehicle, etc. Good. So how was this done historically? So historically, features were hand-engineered. So this is one of the famous figures from the Viola and Jones work. And there, what they wanted to do is identify human faces in images, right? And so they had to handcraft particular filters, like the ones you see here that are black and white, that say, well, this part is typically a little more darker than the part below. And so if we find that sort of pattern, there's a face in the image. Obviously, this has, deep learning has surpassed that significantly. And the main reason why deep learning is, achieving state-of-the-art in a lot of these different applications is because we no longer hand engineer these features. And so errors are not propagated through that model. Instead, we leave the model to learn whatever features it thinks are best for achieving that task. And so we model a mathematical function that governs the entire learning process of this model such that it achieves a specific task, for example, identifying that there is a pedestrian crossing the road. And then we leave the model to learn what features it thinks are most important to achieve that high accuracy on that predefined task. So does that mean that engineering has gone away? Not really. We no longer engineer features, but we still engineer the architectures that we train. So we need to specify, how many layers is this network going to be? How many neurons are in each of these layers? How are they interconnected together? So there's still engineering in the process. It's just, not in the features anymore. I will now present some state-of-the-art deep learning applications, but I will also present some of the ethical concerns related to each of the applications that I'm going to talk about. So I'll start with authentication, okay? So now we can use deep learning to unlock our phones, right? Using an image of our faces, we can use deep learning to sign us into particular apps that we use on our digital devices. We can use deep learning to gain access to restricted access areas to which we are granted access. And so all of this is great. It's a great, technology that would allow us to get into these particular predefined, I'll call them functions for now. Good. But research has also shown that we can add imperceptible noise to images and such that we can make these deep learning systems see something different in these images. So here we have an image of a panda. We add some imperceptible noise. The noise here looks, not really imperceptible, but we've highlighted it significantly so that we can visualize it on a slide. But adding that noise, we still see the result as a panda image, right? So to the human eye, it still looks like it's the same image. But by adding this imperceptible noise, we can actually fool the deep learning system into thinking that this image has a gibbon in it instead of a panda, all right? What does that mean? Well, this means that if we carefully handcraft a sticker, place it on our face, we can also fool an authentication system and get in somewhere where we shouldn't, right? What does that also mean? It means that we can carefully design a sticker and place it on a stop sign in a road such that the autonomous vehicle would no longer recognize this as a stop sign, okay? We call these adversarial attacks, okay? Good. The next application I'll talk about is that deep learning enables the generation of deep fakes. Okay? Now, deep fakes have been always, are always a bad thing or a negative thing, but here I'm going to show an example where it can actually have a legit application. So say I'm a hair dye company, I think this wasn't advancing pretty well. Say I'm a hair dye company, and I'd like to create an app where users could upload an image of themselves or take an image of themselves on their phones, and then they could select the hair dye color, and it would update the image to show them, which particular hair dye they would like to purchase, right? Legit application. Now, the only issue, the other side of the coin, is that this is a very powerful image manipulation technique that can be used to generate non-consensual images, right? And so there has been research that allows us to watermark our images, and I'll very loosely say watermark our images, such that they are not subject to such manipulation. So this purple bubble we have here that says deepfake disruption is basically an algorithm that has been proposed to protect images. The image still looks the same, but to protect images such that if this image was a subject or was input into a facial manipulation system, you would get a disrupted output. You basically cannot manipulate that image. I could watermark, for instance, my image before posting it on the Georgetown website, for example. There's a caveat, though. These deepfake disruption systems are designed for particular deep learning models. And as new models come out, we need new deepfake disruption algorithms to go with these models. So it's really a cat and mouse problem where, you know, we have to keep up to pace with all the new models that are being generated. Good. Now, another application for generative models that seems, very benign is using ChatGPT to say something like, I want to start a herb garden. Can you please help me get started? Right? So that's a great application. You would get some sort of summary, right? Aggregate summary. You can then decide what you want to follow out of that summary, or, you know, if you would like to do something different. But then I asked ChatGPT to generate an image of a room with no elephant, okay? And I got this, okay? Now there's one problem. There isn't just one elephant, there are two, okay? And so, you know, for human feedback, I noticed there are two elephants, and so I wouldn't use this image with that caption. But we use these systems significantly by using their automated APIs. And so we would search such things and accompany whatever labels we used for searching with the output image in an automated way, creating thousands and, you know, if not millions of images and storing them in data sets for, say, computer vision research. And so that could very easily spread misinformation because of this, you know, incorrect association that has been done there. I'll show an example of a video. This shows you how noise can be changed using deep learning models gradually in order to get an image. Yes, it starts from pure noise, so you can imagine the different possibilities, how many images we can get as a result, you know, an infinite number of outputs, because it all starts from that noise image. What other applications? Another AI application is personalization. Now, let me give you a flavor of this. Using your phone to take a couple images of your pet from different angles, and then using that as an input to a personalization app that would then enable you to picture your pet swimming, sleeping in a bucket, getting a haircut, or even on the moon drinking water from a bright orange Stanley tumbler. Okay? So you could do that very, very easily using such apps, such technology. Here's another example of personalization. Assume you have a photo, you upload a photo of yourself, and then you upload a second photo and say, I would like myself in that location, right? So Brighton Pier in this case. And I would like myself performing my face, performing that particular facial expression, okay? And then you get such a result, okay? So it's really cool. You can produce a lot of great output. It helps designers. It helps those who think they're not so creative to actually generate creative output. So it's great if I would like to edit my own photo, right? But it also enables non-consensual generation of images, and of course these non-consensual generation of images could be very quickly propagated on social media, okay, causing harm in some cases. The next application I'd like to talk about is combining concepts, okay? So these deep learning models have been exposed to a lot of data. And in this data, in these images that are out there on the web, there are cakes. There are also images that show ice and images that show fire. But there are, I doubt if there are images that show an ice cake or a fire cake. But because these models have been exposed to these concepts separately, they are able to generate images that look like this. Okay? Another example, if you give it an image of a horse, you can ask for, an Oreo horse or a red velvet horse. I'm pretty sure the models haven't seen these examples, but they know what Oreos look like and on desserts, and they know what horses look like, and so they could combine such concepts. What's the other side of the coin? Such models, unfortunately, can be used to generate child sexual abuse material, for example, nude children. Why? Well, even if the models were not directly exposed to images of nude children, because of all the filtration that happens, with the help of search engines, etc., they could be exposed to the concept of a child playing, at the park, and then exposed to the concept of nudity from some photos in a museum, right? And these models are very good at combining such concepts together, even if they haven't seen a single example that does combine these concepts together. This is a photo I took of the Boston Harbor. I uploaded this onto, in this case, ChatGPT, but there are now several other tools we could also use. And I asked it to style it in Van Gogh style. Okay, and this is the output I got. You could even, ask for a better output if you would like, or an alternative output image. Which is great, because this allows us to, keep the art of those who cannot be among us nowadays. But obviously, it raises many, many, many copyright issues as well, right? If I were an artist today, would I like my, style of art to be readily available for everyone? Would I like to first generate and approve this art before, having it be distributed under my style? A lot of questions over there. Good. Most recent research has been significantly working on erasing concepts from these state-of-the-art generation models, which we call diffusion models. For example, there's been work that would like to focus on erasing nudity, the capability of the model to produce nude subjects. And then another example is being able to generate art that's not for a particular artist. So for example, erasing the artistic style of Van Gogh, not being able to generate or style your image using Van Gogh style. And it's possible that we could have some sort of central system where people register their art, for instance, and say, I would like this, like NSFW nowadays, if you're familiar with that. So an artist or a celebrity can go and say, I would like, my image not to be, I would like, let's say, one of the leading companies, Google or OpenAI, to not be able to generate my identity if somebody prompts the model to do so. So that could be an option, and in that case, such models could be used. You can also train these models to erase objects as opposed to erasing a particular style in the work. Now, unfortunately, some of these proposed concept erasing techniques have also been attacked, and new ones are being developed, all right? So very similar to cybersecurity, if you like. This is really turning into a cat and mouse problem where, there's an attack that's proposed, but then there's another defense that helps against it, and that's the state of the field at the moment. I will wrap up with one more example. So I asked GPT to give me an image of a doctor. I asked GPT to give me an image of a nurse. The output looks great, okay? I didn't necessarily say that I wanted the images to be photorealistic. You could. But if you ask it to generate a doctor 10 times and note how many male doctors you get, and then ask it to generate 10 nurses, and note how many female nurses you get, you will see that there is generative bias in these models that has been learned from the implicit, biases that we have out there. So I hope I've given you a quick overview on state-of-the-art of deep learning models, and also the other side of the coin and the ethical implications related to that. Thank you all so much.